time now to start looking at the actual circuitry on the VAM PCB, the circuit that we're going to be setting the values for. And we'll start by looking at something we haven't looked at before, which is the value of this resistor here, R45. I've set it to be nominally 470k, but you can choose a different value if you like. That's there to enable us to test the amplifier. The problem with this amplifier is that we're trying to test an amplifier to see what the gain is when the input is 1 millivolt RMS. Now we can't produce an input of 1 millivolt RMS from the test equipment that we have in the lab. It's too small a voltage for the function generators to accurately produce. So we've built what is effectively a potential divider. You put a small signal in through the test input socket here, J7. Make sure that switch 4 on switch block 7 is closed so that the signal comes through to R45 and then goes into one of the two differential inputs in the VAM. Don't fit anything onto the other one, which means that the other one is effectively grounded. We've now effectively built this. Provided R45 is much greater than our input impedance, then we have a potential divider here which will make its output, that is the voltage across Zin, much smaller than the input that we put into J7. And the output of the potential divider, that's the voltage across Zin, is effectively the input voltage going into our differential amplifier. We can now afford, provided R45 is large enough, to have quite a large input signal, maybe 100 or 200 millivolts RMS going into J7, and the function generators in the lab can easily produce an accurate output amplitude of that magnitude. Right. So, having selected R45 and 470k would be a reasonable value, we could then determine what the ratio is between the signal on J7 and the signal on Vin by just putting in a large signal at J7 and measuring the voltage at this point here. Maybe if we put 1 volt in there, we might read about 20 millivolts there, perhaps. Once we know the ratio, we can work out what input voltage there we would need to produce 1 millivolt across here. Has to be done by calculation because it's quite difficult to measure 1 millivolt RMS accurately. It's too small a signal for the oscilloscopes to be able to accurately measure either. So we work out the ratio of Vin to the value on J7 with a very large voltage on J7. Work out what voltage on J7 we would therefore need to produce 1 millivolt, and just trust that the circuit is linear and would still work. Which it should, provided all of the measurements that we've taken show nice, clean, undistorted sine waves. We have a look in a bit more detail about the input circuit here. There's a few other components that I should mention. R48 and R49 are there to help set the input impedance. They don't uniquely set the input impedance because some of the current will flow through these DC blocking capacitors into R47 and on into the circuit that way. So the input impedance is actually set by the values of R48, R49 and R47 and R19. But provided R47 and R19 are greater than R48 and R49, then the majority of the input impedance is determined by the values of R48 and R49. Trouble is, you can't set R47 and R19 very large values because then you couldn't get very much gain out of this first stage without setting R23 and 24 to ridiculously large values. And if you did that, then you might start running into problems with the parasitic capacitors across those resistors, meaning they don't behave like good resistors at very high frequencies. As a rule of thumb, try and keep all of the resistors that you use for setting the gains somewhere in the range between 1k and 1 meg. We've got an inductor here, which is there to just try and quieten down the power supply. PSRR stands for power supply rejection ratio, and it's a measure of how much of the noise, the variation on the 3-volt power supply comes out of the op-amp's signal output. We've got C71 and C72, which initially don't fit. They're there just in case you need them later on. If you make very high gain amplifiers like this, it's quite easy to make oscillators by mistake. If that happens, if your circuit starts oscillating, there may be a need to fit small values of capacitor here in order to limit the gain at very high frequencies and stop it oscillating. Hopefully will not be required. And C73 is an R82 is there as a low-pass filter on the mid-rail output, because again, any signal on the mid-rail output there, any variation in that is going to get into this front-end stage, get multiplied by almost 1,000 before it gets out of our differential two-stage amplifier. So we have to try and keep all of the signals at this input stage as quiet and clean and noise-free as possible, because any small amount of noise in the signals here gets multiplied by 1,000 before we start to listen to it. The gain of this front-end stage is, as we've seen before, set by R23 and R24, which should be equal, and R47 and R19, which should be equal, but don't forget to check that the resistors are equal and closer in tolerance than their 1% limits. Otherwise, you'll end up failing the common mode rejection ratio specification on the amplifier. The output of that first stage amplifier then goes through this low-pass filter of R72 and R69, which, as the slide says, gets rid of some of the very high-frequency noise outside the human hearing range, and again helps stop the amplifier from oscillating. The advice in the lab book is just set it so that the pole's break frequency is somewhere like 100 kilohertz or so, and then forget about it. And then we have the output amplifier stage here, and this is the second stage of gain. C67, it's there again just to stop the amplifier oscillating. The gain of the amplifier is set by R26 and R25, or if switch 5A is closed, R26 and R73 in parallel, and R25. And that allows you to select two different gains. One for things like microphones, which have very small input signal levels, and one more suitable for things like synthesizers, which have much greater signal levels coming in on their differential inputs. C68 is there so that the gain of this second stage at DC is just 1. At DC, the capacitor here will have an infinite impedance, which means the gain of this non-inverting amplifier is just 1. So none of the DC signal that comes out of the first stage will get through the second stage. Why, you may ask, would there be any DC output of the first stage? Well, that's because, again, op-amps are not ideal in the real world, and they do have a small offset voltage. You don't want the offset voltage to be amplified up by 1,000, because it's perfectly possible that the input offset voltage might be, say, 1 millivolt, and if you amplified that up by the full gain of almost 1,000 of our two-stage amplifier, you would end up with an offset voltage of about 1 volt. So instead of an oscillation centered around the mid-rail at 1.6 volts, you would have an oscillation centered around possibly 2.6 volts with a 1 volt offset. Well, if it's set around 2.6 volts, it doesn't have very much headroom. It's going to crash into the 3 volt voltage power supply of these op-amps quite soon. It's really going to limit the maximum amplitude that you can have. So we want to stop that DC offset building up, and that capacitor is a good way of doing this. Right, that is how to set the gain and a quick introduction to all of the components that are in the differential amplifier on the VAM. One suggested approach to the design would be to do this. First of all, ignore the capacitors and the gain bit bandwidth product of the op-amps and just design the resistors to give the gain required. Because provided you've got the gain reasonably well distributed between the two stages, the gain bandwidth product of the op-amps isn't going to cause you a problem. Set 73 to a huge value. That's this one here. By huge value, something like 10 microfarads would be fine. At 10 microfarads, the effect of that capacitor at audio frequencies is negligible. Select C57 and C58. Right, now I haven't mentioned this before. That's these two capacitors here. That's the DC blocking capacitors, which allows the inputs here to be centered around 0, whereas the signals inside the VAM that are being processed by the op-amps are centered around the mid-rail voltage of 1.6 volts. The calculation for what those values should be is exactly the same, well, pretty much the same as the calculation done when we were looking at the corresponding capacitors in the summing amplifier. So go back and have a look at that lab. It's a very similar calculation to do. Set C68 to a practical value. C68 is this one here. And again, there's no real maximum value than that, other than what's determined by cost and what fits on the VAM itself. So a value of something like 10 microfarads would be equally appropriate here. And then set C69 to meet the high frequency specification. C69 is that one there. I think I mentioned before, if you set the pole break frequency of this RC network here to around about 100 kilohertz, it's not going to have any significant effect at audio frequencies. You should be fine. And then, when you've got all your values, check that they work. And a good way to do that is to use simulation. There's a simulation model of the VAM as one of the presets in the simulator. It's called VAM diffamp 2 in the VAM design preset group. And it looks like this. And up to you, set all the values of these resistors and capacitors in your design to ensure that you do get the gains required, which change as required when you close the switch. So for 1 millivolt input there, we should be getting out plus 2 dBu or minus 20 dBu. That's either 976 millivolts or about 77.5 millivolts, depending on the switch here. That the gain is constant within 0.5 dB across the range from 40 Hz to 20 kHz. And you can see that these particular values are pretty diabolically useless, since the gain is absolutely not constant between the range of 20 kHz and 40 Hz. In fact, nothing like it. And they're certainly not anywhere near the values that we would want of nearly 1 volt output here when the switch is open. So, quite a lot of work to do to set those values to something that would actually work. But if you can get the simulation showing that things work, you should be very confident that if you put those values on the board will work fine. Good luck.